All right, everybody, welcome to another video lesson on differential equations. So this time, we're going to be getting into a different type of a first order differential equation, and they are called linear differential equations. Okay, so without further ado, let's get started. So here is a the formulation on how to solve these types of differential equations. So the form, it's going to look like this, okay? So you have dy dx, right, as its own quantity, plus some function in x, like this, we'll call it p of x times y, okay? And this equals to some function of x, we'll call it q. All right. So a first order linear differential equation will always look like this. Okay. You have a single quantity dy dx, right, plus another quantity p of x times y, okay, and it equals to q of x. And y is just some function in x, right? And we're trying to solve a general solution for y of x, okay? So the goal here, and so the goal is to find a general solution for y of x. Okay, so here's the idea behind figuring out the general solution. You'll have what is called an integrating factor. I'll call it I. So this is what's called an integrating factor. Okay, integrating factor. And what this will look like is e raised to the integral of p of x dx, right? So that is what it will look like. So let me rewrite this just a little bit more clearly. So I is what's called the integrating factor. And I, once again, will look like e raised to the integral of p of x dx. So p of x being the exponent number, right? P of x being the exponent number. Okay. So you can rewrite this as e raised to the capital P of x, where the derivative, the capital P of x is just the regular P of x in your function here, right? So what we're going to do now is we're going to multiply both sides of this differential equation by this integrating factor, right? And what turns out is we'll have an equation that looks like this. So I'll have e raised to the integral of p of x dx times dy dx, okay, plus p of x times e raised to the integral of p of x dx times y. And this would equal to q of x times e raised to the quantity of the integral of p of x dx. So it looks like this, right? So the next step is, if you notice on the left-hand side of this equation, so the left-hand side of this equation, you can use the product rule, but the product rule for derivatives. But you have to use it backwards. Okay, so this left-hand side, you can write this out as d dx of, in this case, y times e raised to the integral of p of x dx, right? You can also rewrite it like that. And then this right-hand side is just equal to q of x times this exponential quantity, right? Okay, so then what we can do is integrate both sides, right? So if we integrate both sides, this left-hand side will become by the second part of the fundamental theorem of calculus, right? Integrating derivatives would be equal to the function itself. So you'll have y times e raised to the integral of p of x dx, and this would equal to the integral of q of x times this quantity. I know this looks kind of messy, but we're actually almost there, right? If we divide both sides by y, we will get what a general solution for a linear differential equation should look like. And it should look like this, right? Y of x is equal to, well, this integral, q of x times e raised to the exponent number of, in the integral of p of x dx, divided by the exponential e raised to the integral of p of x dx, and then plus a constant, c, right? And in your textbooks, they label mu of x as this exponential number, right? But nevertheless, that is the general solution for a first order linear differential equation, okay? It should look like this. And then I actually did an overview of the steps to solve a first order linear differential equation, but right here, this is how you proceed with the steps. So you're going to write out a first order differential equation in standard form. So this is a standard form of a linear differential equation. Then mu of x, they labeled this as the integrating factor. So the integrating factor was e raised to the integral of p of x dx, right? It's not an s, it's an integral. So, oh, Jesus Christ. So, yeah, so this would be e raised to the integral of p of x dx, right? Next, you're going to multiply both sides by this integrating factor, mu of x, all right? And then you're just going to use the product rule for derivatives on the right-hand side. So this step right here, they use the product rule for derivatives. Okay, product rule for derivatives. Okay, and then you're just going to integrate both sides to get this expression. That's dx, and you can figure out what the general solution is. So mu of x times q of x divided by mu of x plus c. All right, so that's the general solution of a first order linear differential equation. And so we can arrive at an important theorem in differential equations, and it's what's called the existence and uniqueness theorem. Existence and uniqueness of a solution. So for a first order differential equation, if we have p of x and q of x as a continuous functions on an open interval from a to b that contains the point x naught, so the function is continuous on an open interval a to b that contains x naught, then for any initial choice of an initial value y naught, there exists a unique solution y of x to this differential equation. I should say initial value problem, right? You're invoking the initial condition in that case. And it's given by this general solution that we found. Okay, so we'll arrive at what's called the existence and uniqueness of a particular solution of a linear differential equation. Okay, so let's look at some examples. All right, so I want you to look at these following examples. So these are initial value problems. So I want you to solve for the following, right? So we have in part A, dy dx plus 4y equals e to the minus x. And we have an initial condition of when x is 0, y is 4/3. Okay. And then in part B, we have sine of x dy dx plus y times cosine of x equals x times sine of x. And our initial condition here is that when x is pi over 2, y is 2. All right. So I want you to pause the video and work out these examples and see what type of solution you come up with. Okay, so I assumed you worked on this two examples. So let's work these out. All right, so if I let me see, can I zoom in here? Okay, there we go. So we have a linear differential equation here. So what we want to do is so p of x is 4, right? And so we have this integrating factor, e raised to the integral 4 dx, which equals to e to the 4x, right? And so if we multiply both sides by this equation by the integrating factor, we'll have e to the 4x dy dx plus 4 times e to the 4x times y equals, so in this case, e to the 3x, right? Just adding exponents. And then the left-hand side, so this would equal to, so this would mean the left-hand side is just the derivative of e to the 4x times y, and this equals to e to the 3x on the right-hand side, right? Then the next step is to integrate both sides. So the left-hand side will be just the quantity itself. So it'll be e to the 4x times y. And this equals to the integral of e to the 3x times dx. Okay. Okay. So so we'll have e to the 4x times y, and that will equal to 1/3 e to the 3x plus c plus a constant, right? And so we'll have y of x is our general solution equal to 1/3 times e to the 3x plus a constant over e to the 4x, right? So this here is our general solution. Okay. So now our particular solution, right? So we know that since if x is 0, y is 4/3. So that means when x is 0, we'll have 1/3 times e to the 0, which is 1. We'll have plus c over 1. That equals to 4/3. So what that implies is that 1/3 plus c, if we do cross multiplication, is equals to 4/3. And so c is 1, right? And so our particular solution would equal to, so yeah, I'll just write it out like this. 1/3 times e to 3x plus 1 over e to the 4x. Oh, this should be y of x. Okay, y of x. So that's your answer. And now part B says we want to look at this differential equation, all right? So we want to write this equation out in standard form, right? So if we divide both sides by sine of x, right? Sine of x, and this is by sine of x, we'll have the linear differential equation in standard form, right? So we'll have dy dx plus cotangent of x times y equals x. Okay. So we have it in standard form. Yes. Okay. So now we need to incorporate the integrating factor. So we have the integrating factor, e raised to the integral of e times cotangent of x dx, which would equal to, I'll drop my pen, e raised to the natural log of the absolute value of sine of x. Okay, that's the antiderivative. So that would equal to just sine of x, right? So this function is defined on 0 to pi over 2. I'm sorry, where um, cotangent is defined, right? So um, uh, so typically we want to use uh, 0 to pi, right? That's the domain of cotangent, right? So and we know that it's positive on 0 to pi, right? Okay, so if we multiply both sides of the differential equation here by sine of x, what we will have is that we'll have sine of x times dy dx plus cosine of x times y. The hell just happened? Um, times y, and this equals to x times sine of x, okay? And so on the left-hand side, we can just express this as d dx of sine of x times y, and this equals to x times sine of x, okay? Next, if we integrate both sides, well, what this turns out is that, so we'll have, y times sine of x itself on the left-hand side, and this equals to the integral of x times sine of x dx. Okay. Now, the right-hand side, we're going to use integration by parts, right? So use integration by parts here. So there's a method called tabular integration, right? The u goes on the left and the dv goes on the right, okay? And so you choose u as the function that is simpler to differentiate, so there's no oscillation going on. So if you like differentiate sine of x, right, it's cosine of x, and then with the derivative of cosine of x is minus sine x, and then you get minus cosine x as its other derivative, and you're back to, sine of x again, right? But when you differentiate like a power on x, let's say x to the fifth, right, we'll have 5x to the fourth, and then 20x cubed, and then 60x squared, and then 120x, and then 120, and then 0. So with a power on x, it terminates to 0 at some point. Okay. So we want to choose a function such that if we differentiate it, its derivatives will terminate at some point, right? So typically, so let me erase this real quick. So we want to choose a function whose derivatives terminate at some value, right? At some value where the derivatives will be 0. Okay. So with integration by parts, it only works if you have a product of two functions, f of x times g of x dx. Okay. And then to choose, so integration by parts, the formulation, right? UdV is equal to UV minus the integral V times du, right? And then the formulation to choose U, I like to use this acronym called LIATE, right? So L stands for logarithms. I stands for inverse trig functions. A is for algebraic. So different powers on x, right? And so on. T is regular trig functions, and then E stands for exponentials. Exponentials, okay? So that's the strategy for integration by parts, and that should have been reviewing in Calc 2, right? So we're going to use that here, okay? So we have a product of functions, right? X times sine of x in our integral, okay? So let me just erase all of this here. Let me choose a bigger one. There we go. Okay. So, oh shoot. Okay. So I want to choose u as x and then dv as sine of x. So so on the left-hand side, we differentiate x. So it'll be 1 and then 0. And then we integrate v on the right-hand side. So it'll be negative cosine and then minus sine of x. Okay. And then to use this tabular method, we will multiply the terms by this way. So we go diagonally and we oscillate every time from positive to negative, right? So the integral of x times sine of x dx, this would equal to negative x times cosine x, okay, minus 1 times negative sine of x. So it'll be minus sine x. And then it'll be times 0. Okay, so that would terminate at that point, right? And then you're going to add a constant plus c. Okay, so what this equation becomes is we'll have y times sine of x on the left, and this would equal to minus x cosine x plus sine x plus c. And so the general solution, okay, so the general solution y of t, this equals to minus x cosine x plus sine of x plus c divided by sine x. Okay. So hopefully that makes sense. So right here, this is the general solution. Oh, Jesus. It's supposed to be an S there. General solution. Okay, so now we're going to incorporate the initial condition, right? If x is pi over 2, y is 2. Okay, so what that means is if x is pi over 2, cosine of pi over 2 is 0, and then sine of pi over 2 is 1. So we'll have 0 plus 1 plus c over 1 equals 2. So what that means is we'll have 1 plus c equals 2, and so c equals 1, right? And so we'll have our particular solution as y of x, not t, y of x is equals to minus x cosine x plus sine x plus 1 divided by sine of x. So that's your answer. Okay. Last but not least, I want to go over an application problem that reflects on linear differential equations. Okay. So, so this will reflect on what is called a stirred tank. A stirred tank problem. We'll look at this problem in the future, but it's probably best if I go over this in earlier than later. So suppose we have a brine, a tank that contains suppose we have a tank that has brine that has 0.2 kilograms of salt per liter, and it runs into a tank initially filled with 500 liters of water. Okay, and it contains 5 kilograms of salt. The brine enters the tank at a rate of 5 liters per minute. Okay, the mixture, kept uniform by stirring, is flowing out at a rate of 5 liters per minute. Okay, so this is the figure here. And A of t denotes the amount of salt in the water for time t. Okay, so the objective here is we want to figure out the amount of salt in the solvent. The solvent is just the mixture, right? After 10 minutes of mixing. Okay, so what a mixing problem is, so we want to look at the time, the rate of change of the amount of salt in the solvent with respect to time, right? And so all that is we have to calculate the rate of change of the solvent going in minus the rate of change of the salt going out. So once again, we will look at the rate of change of the salt going into the tank minus the amount of salt going out of the tank. Rate in minus rate out. And so here's how we would do this. So the rate that's going in, we know that dA dt, well, this would equal to the amount of water that's going in. Well, the amount of water in liters is just 5 liters per minute. Okay. So this here is the water times the amount of salt that's going into the tank per liter. So this is 0.2 kilograms per liter. So this is the amount of the salt. Okay. Minus, minus. So this is where it gets a little bit tricky. Okay. So we don't know the amount of salt that's going out of the tank, right? We don't know the rate of change of the salt going out of the tank. Okay. But we know A of t represents the amount of salt that is that's in the water, right? So the amount of salt, well, this would be, let's say A of t kilograms per liter. Okay. So A of t kilograms per meter. And So what we want to do is this equation is formulated so the rate that's going in must be the same as the rate that's going out. So in other words, the brine that's in the tank is the same, right? It's uniform. So what we're going to have to do is, so we're going to have, so this is the amount of salt. And then this number here, this will denote the concentration, right? So, so this is the amount of water, or I should say, let me erase this. Okay. All right. So we have the amount of salt times what is called the concentration. Well, it's not concentration. It's actually the amount of water that is going out per unit volume, right? So this is water per unit volume, right? So this would be 5 over 500 liters per kilogram, right? But actually, yeah, I meant concentration. Okay, so right, so let me change this here. Water and salt per unit volume. Okay, that's what I meant. All right, so that unit is called the concentration. Okay, so what we want to know is the amount of salt that's going out of the tank. All right, but it turns out this would be a first order linear differential equation, right? So we can simplify this as dA dt. So the liters will cancel, and you'll have so you'll have 1 kilogram per minute of salt that's going into the tank, right? This should reduce down to kilograms per minute, right? A of T is the weight of the salt, right? The amount of salt in kilograms. So kilograms per minute. So so we'll have minus 1 over 100 times A of T. Okay. And the units here is just kilograms per minute. Right? You should have kilograms per minute in dA dt. Okay, so in standard form, right, we'll have dA plus dt plus 1 over 100 times A of t equals 1, right? So, okay, so that is our differential equation. Okay, so let me zoom out here. And I need to get some more space. All right. And so and from here, we would know how to solve for linear differential equations, right? So, okay. A of t equals 1. The integrating factor would be e raised to the integral dt, which is 1 over 1/100, so that's 100 e to the t. So that's the integrating factor. And so we'll have, if you multiply both sides by this integrating factor, we'll have, so we'll have 100 e to 1 over 100t times the 80t plus. So we'll have okay. And then this left-hand side will reduce down to this function times a of t. Okay, so we'll have that. And then let me erase let me erase this piece right here. Okay. And if we integrate both sides here, excuse me, so we'll have 100 times e times a of t, and this equals to 100 times and then we'll have t over 100 times a of t. This equals to so I'll do this in my head. So the 100s will cancel here, and we'll have another 100 here. So it will be 100e raised to the t over 100. Jesus. Plus a constant. And so a of t, this would equal to c times e to the minus t over 100. And then we'll have plus 100. Okay, so this right here is the general solution. Okay, so we know that the initial condition was when t equals 0, its initial weight for the salt is 5 kilograms, right? And so when t is 0, we'll have, so that's 0, so that's c plus 100 equals 5, which leads to conclude that c is equal to minus 95, right? And so a of t, this should equal to minus 95 e to the minus t over 100 plus 100. And then to figure out the time, figure out the weight of the salt at 10 minutes, a of 10, just plug in t equals 10 into your particular solution here. And then you should be able to get what I got was about 14.03 kilograms. Okay, 14.03 kilograms. So that's an application problem on stirred tanks, which involves solving first order linear differential equations. So hopefully that was exciting. Now onto the fun problem. So I want you to work on these problems for comprehension. These are in your textbook. So, yeah, so hopefully that made sense. So for next time, we'll be looking at um, another type of first order differential equation, and it uses what are called exact differential equations. So I'll see you in the next video. Thank you for watching.